Let's discuss thermochemistry. And in particular, let me define the heat of reaction. So heat can be absorbed or evolved in the course of a chemical reaction. When that occurs at constant pressure, then the change in heat is equal to the change in enthalpy. And so we define the heat of reaction as the enthalpy of the products minus the enthalpy of the reactants. That's pretty simple. We also refer to the two cases of heat out versus heat in as exothermic. Exo means out. That means that the change in enthalpy is less than zero. The heat of reaction is negative. So negative heat means heat released from a system to the surroundings. We also sometimes say that the reaction goes downhill. Heat is produced, or we evolve heat. And so if you like, on an enthalpy scale, which rises from low enthalpy to high enthalpy, the reactants start at high enthalpy, they give up heat to end up at lower enthalpy. If it's the opposite, that is, if heat is absorbed, we refer to that as an endothermic reaction, or the reaction is uphill, the product enthalpy is above the reactant enthalpy. We need to supply heat to drive the reaction. So what's an example? An exothermic reaction might be combustion of methane. So methane gas plus 2 moles of oxygen gas goes to carbon dioxide plus 2 moles of water. Heat is evolved. This is an exothermic reaction. Everybody knows this. You burn natural gas, you make heat. And in fact, the heat of reaction is minus 890.36 kilojoules for this reaction as written at 298 Kelvin. Because we're actually reacting with oxygen, there's another name associated with this. This is a heat of combustion. A critically important endothermic reaction is the water-gas reaction. And that consists of heating carbon, so coal if you like, heating it really, really hot and allowing it to react with water. And when heat is supplied, the reaction will go forward to generate carbon monoxide gas and hydrogen gas. So it's a way to create hydrogen, a useful gas. Actually, carbon monoxide, while a very poisonous gas, is very useful industrially. And so the heat of reaction in this case is not negative, it's positive. That's why it's endothermic, 131 kilojoules at 298 Kelvin. Heat required to drive the reaction. So I'm going to give you a chance to look at a reaction or two of your own and self-assess, and then we'll come back. An interesting feature of enthalpy, a critical feature, is that it's additive. So it's a state function that makes it additive. It doesn't matter how you get from one place to another, it just matters where those places are. And why is that important? Well, if I have heats of reaction for two different reactions, here I've got a reaction 1 and a reaction 2. Reaction 1 is combustion of carbon. Reaction 2 is further combustion of carbon monoxide to carbon dioxide. The first one is exothermic to the tune of minus 110.5 kilojoules. The second one, minus 283 kilojoules. What if I imagine adding these two reactions together? When I sum them, I get carbon, I'll pull that down here, I get 2 oxygens, each 1/2 mole, so I'll pull it down and make 1 mole of oxygen. Carbon monoxide appears on this side and on this side, so that cancels out. I don't have that anymore. And what's left on the right-hand side is carbon dioxide. So carbon plus oxygen goes to carbon dioxide. The proportions are different. And the enthalpy change can be determined as the sum of the two individual enthalpy changes because it's a state function. I'm just interested in getting from carbon and oxygen to carbon dioxide. And so it's minus 393.5 kilojoules. This additivity feature is known as Hess's Law, the fact that you can add heats of reaction to determine the heat of reaction of a new reaction that is the sum of individual other reactions. So a different example, just to sort of drive that home, is reaction 1 is the reaction of phosphorus as a solid with chlorine gas. This is a nasty reaction you would not actually want to do in your home or office, but in any case, in a good industrial setting, you can do it. You can make the liquid phosphorus trichloride. it is exothermic minus 640 kilojoules. Another reaction is to change the proportions, reacting phosphorus, again with chlorine gas, to make solid phosphorus pentachloride. And that is exothermic minus 887 kilojoules. And you might ask the question, what if I react liquid PCl3 with gaseous chlorine gas to make solid PCl5? What would I expect the heat of reaction to be? Well, what we want to do in order to accomplish that is, I need to get phosphorus trichloride over on the reactant side, because here it is as a reactant. So I'll reverse equation 1. I will then add equation 2 so that I have phosphorus pentachloride still on the product side. And I'll need to divide the sum by 2 because when I put 2 phosphorus trichlorides over here and I only want 1 here, I've got 2 phosphorus pentachlorides here, I only want 1 here. So let me just do that. I reverse reaction 1. So now the enthalpy is not negative, it's positive. I'm running it in the other direction, 640 positive. I add reaction 2, minus 887. That gives me this equation. There's a factor of 2 in front of all my reactants. It's minus 247 kilojoules. I divide by 2 so that I only have 1 mole on each side. Minus 124 kilojoules for phosphorus trichloride liquid plus chlorine gas goes to phosphorus pentachloride solid. So simple manipulations, but powerful in a sense, and intimately dependent on enthalpy being a state function. Doesn't matter how you get there, just matters where you are. So in the next lecture, I want to tie all these concepts together and be able to put numbers into reference sources in a way that will be generally useful. We need to standardize our approach to computing enthalpies because while we are quite good so far at computing enthalpy changes, we aren't very good yet in assigning a specific value to an enthalpy, and sometimes that can be quite useful. So in fact, we will look at the concept of standard enthalpy in the next lecture. However, having talked about exothermic and endothermic reactions, I, as a chemist, am inspired to do at least one more exciting exothermic reaction. So we'll slot in a demonstration here and look at a pretty interesting exothermic reaction, much as thermite was a pretty interesting exothermic reaction. And then finally, we'll look at standard enthalpy. For the announcement video for this course, I did one of my favorite reactions, a thermite reaction with iron and aluminum, presenting it as an example of a highly exothermic reaction. And in one of the first lectures, we looked at just how exothermic it is and why the temperature increases enough to melt iron. Now I'd like to do another of my favorite reactions that's also exothermic. Indeed, just about as exothermic on a per mole basis as the thermite reaction. Transformations belonging to the general class of thermite reactions all involve the transfer of oxygen from a less reactive metal to a more reactive one, with the driving force being formation of the more stable oxide. Iron and aluminum are the most commonly illustrated partners for such a process, but other possibilities abound. In this case, we're going to observe the reaction of elemental magnesium metal with carbon dioxide. While carbon is not a metal, the same process of transferring oxygen from a less oxophilic species to a more oxophilic species will take place in this reaction. From the known heats of formation, we can determine that magnesium metal should react with gaseous carbon dioxide to make magnesium oxide and solid carbon, that is, graphite, with the liberation of 812 kilojoules per mole. In practice, the reaction is a bit more dramatic if instead of gaseous carbon dioxide, we use solid carbon dioxide, that is, dry ice. So, we have here a slab of dry ice. In this lower block of dry ice, we've chiseled out a small hollow, and we're going to fill that hollow with some shavings of magnesium metal. In a moment, I'm going to light those shavings with this torch, at which point they'll begin to burn in the air. To begin with, they'll actually react with oxygen in the air, as that too is an exothermic reaction and the oxygen is readily available. However, we're then going to cover the burning magnesium with another slab of dry ice. And once all the oxygen is consumed, the magnesium is going to begin burning the dry ice in a fashion that is reasonably dramatic. Shall we give it a try? I'm now lighting the magnesium turnings. And they're off. Wow! Did you see that? Once the dry ice began to serve as the oxygen source, it lit up brilliantly, and the heat caused some wonderful sublimation and condensation of water vapor in the air. Let's also take a look at the residue here in our remaining hollow. Do you see the black, sooty powder? That's elemental carbon mixed with the more gray-white magnesium oxide. Besides being a pretty example of an interesting exothermic reaction, this demonstration should also have shown you why you do not want to use a carbon dioxide fire extinguisher to put out a magnesium fire, because it won't. Indeed, burning magnesium will also strip oxygen from both water, which we could call hydrogen oxide, and sand, which we could call silicon oxide. So, are you wondering what's the best approach for putting out a magnesium fire? Pretty much backing up and waiting may be your best strategy.